In the first part of this tutorial concerning the p-n junction, I show you how to create a two-dimensional structure for a p-n junction using the GMesh program and writing a geo file for this p-n two-dimensional structure. Now in the second part I'll show you how to use the input file, which is very similar to the one which I showed you in the first tutorial concerning the 1D structure. Of course, here the situation is a little bit more complicated and we will see some new issue. Okay, at first we have in the first line the device. You have to define the device, the structure we are using. So you have in this case we specify the mesh units, so 1 to 10 to the minus 6, so we are in micrometer, and then you have to specify with the mesh file we are using, which is the one we created, pn2d 0.1.msh. Of course you can choose whatever name you prefer, as long as you choose the same file you have generated with GMesh. Okay, here in the device now we have to specify the region. If you remember, we had two surfaces, two regions, the N region and the P. So here we have to define the same through as in the geo. There we have the physical surface and type P-type. We have to be careful that we have to use the same name we specified there. So N region and P region. Which region they are. Here we can specify which kind of structure. So we have silicon, which is zinc blended ZB structure. This is the crystal structure of the silicon, and here we can specify the X, Y and Z growth direction. These are the Miller index, of course, for the crystal structure. Of course, this is the default structure for zinc blended 10001 in the 3 direction for this zinc blend structure. Then the material, of course, and then since we have as I said, an N region and P region for this junction, we have to specify the doping. So for the N we have the type donor, we have the density, so 1 to 10 to the 11th, and then we can specify the level here, 0.225. Very similar here, of course, we have the acceptor for the P type. So here we specify the region. And then if we go down, we have again, as in the 1D for the silicon bulk, we have a drift diffusion and a sweep. It's very similar. Again, the last module is the most important, is the simulation. We can specify also the temperature. In that case, we did not specify. By default is room temperature, so 300 Kelvin. Here we can put the result part of the output. Here we put output 100. I will tell you why 100. Here we have the format for the 2D. This is VTK format. It's the format which Tiberlab used by default for two-dimensional results. It's a file with some array that could be opened with some specific problem, as for example open access paraview, which you can use for your analysis of your data. Okay, so as in the first tutorial here, so we have sweep 0, which is the name that we choose for sweep. Sweep is by default, we cannot change this, the name of the module there defined in Tiberlab. Of course you can, for your reason, for it would be helpful for you to choose a particular name. In this case we put sweep 0, and again sweep 0 call the drift diffusion. In this case also drift diffusion we decided to give another name, not the default drift diffusion, but just DD in order to shorten. So here we solve only sweep from the main simulation module, but sweep of course will solve itself the drift diffusion. Again we have a contact cathode, which is the variable which you have here in the drift diffusion, which is a value that it will sweep from 0 volt to 1 volt. case we have 100 steps, so not 10 steps as for the bulk, but we have 100 here. The name, the reason of the name output 100. Of course, we can, if you want to do it with, for example, 50 instead of 100, then you can just change this value here to 50, and then you can just to have another output in order not to delete the previous result. Because if you choose the same name for the output for a second simulation, of course the program will write will overwrite the result on the previous file, so you will lose the previous result. So it's important, it's useful to change the name of the output if you want to run a different simulation with some different parameters. So again, from 0 to 1 in 100 step, and you saw the 3D fusion. Here it's been more complicated. You have the name, we said 3D fusion. Region is okay, here it's whole because M and P, these are all the regions we have in the system. We plot here, we can plot a lot. Basically we have almost all the variable here, the contact currents, the internal quantum efficiency, the current density for the total, the electron, the hole, the density of the electron, the density of the hole, the electric field, and so you have all this specified in the manual of Tiberlab. Here you have some parameters for the solver that you can specify. Of course, these are not necessary in the sense that you have some default parameters, but you can have a look in the manual how could be better to speed up, for example, the solution of the problem. Here we have some physics for the electromobility, which is type constant, both for the electron and for the hole. Of course, you can choose a different one. We will see in another template, in another tutorial. And again, you have to specify the boundary condition for the anode and the cathode. So it's type harmonic, and then you have the voltage, which is by the name of the variable Tiberlab use, and then you have to put equal to the variable which is defined, of course. In this case we need only the cathode, which is specified by the sweep. Here, for each of the 100 simulation that you will have in this sweep, the module sweep will give to the diffusion a different value for this variable which will be used in the simulation. And then you can run the program, and you will have at the end a folder with all your results that you had here in the diffusion in the plot. So this is finished this 2D simulation. In the following tutorials we will see again something more complicated for three-dimensional structures, but of course we will use what we saw in these first two tutorials, which are the basis for our structure and for our input file.